So this instrument is Autocollimator. So usually this is used to find the straightness of surface. Straightness means deviation from a straight horizontal axis. How much it is deviated from the straight horizontal axis. This is also used to find out the flatness of the surface. So for straightness we require only one axis, but for flatness you have to minimum two axes you require, x and y. Then from that you construct a reference plane, and from within that reference from the reference plane, what is the deviation of the plane you have to calculate. So parts of the instrument is actually this is the collimator part. Is passing a parallel beam of light, and this light falls on the reflector. So this is the surface plate. We are going to find the straightness of the surface plate. So this reflector is resting on the surface plate, and so this is not this is a front polished reflector. It's not glass, it's a metal reflector. So this will avoid double reflection. If we are using a glass reflector, it will produce a double reflection. To avoid that, we are using metal polished reflector, and this is mounted on a base. Actually these two are separated. This is one portion and this is the base portion. This base is 0 to 50 mm. This is the width of the base portion. So this is calibrated for 1 second tilt of the reflector. 0.25 micron is the surface variation. So this is the principles of operation. Suppose this producing a parallel beam of light from the focal point, is producing a parallel beam of light, and this is the reflector. If it is exactly vertical to the optical axis of the collimator, reflected light is also falls at the focal point. So you get a 0 reading. But since the surface having irregularities, the reflector will be in a tilted position. So this will tilt like this. So reflected image at the focal point also shifted from the initial positions. So we are going to measure the angular tilt of the reflector for each position. Position means first position is 0 to 50, position 0 to 50. Again second position, from the scale you note, move this to 50 to 100. Then again you note the reading, then move this to this position 100 to 150, like that. So this is the tabular column, position 0. 0 means when the reflector are exactly vertical to the optical axis. Then from the first position 0 to 50 we will get one reading, angular reading you get from the head scale here. This is a vertical scale. By rotating this we can get the reading here. This is the eyepiece. So this is the internal construction. This is the head scale, this one, this is eyepiece. So this is having this micrometer having one graticule, that is called eyepiece graticule. This is the eyepiece graticule. This eyepiece graticule is inscribed on the plate of this micrometer. So when we are rotating this line move up and down like this one, and one more graticule is also, that is called target graticule. Target graticule is inscribed on the slide here, this one. Then that image falls on the beam splitter here, then reflected along the axis falls on the reflector resting on the surface, then reflected back. So this target graticule is falls on the reflector, reflected back and we can see, view through the eyepiece. So in the eyepiece field we can see, without the reflector we can see the eyepiece graticule, but after placing and aligning the reflector we can see eyepiece graticule also in the same field. So eyepiece graticule is here, this is the target graticule. Then we have to adjust this one, this micrometer head, so that this horizontal line of the target graticule comes in between the twin line of the eyepiece graticule, like this, and then this vertical line should coincide with the vertical line of the eyepiece graticule. For vertical line coinciding, we have to tilt like this, sideways tilt, and horizontal line coinciding, we have to rotate like this. So in the final adjusted position, this is the final adjusted position. This comes in between the twin horizontal line, these two vertical lines coinciding. So after that, after aligning like this, you note the reading here, reading from the scale. So for each positions of the reflector, you adjust the vertical line and horizontal line. Horizontal line by adjusting the micrometer head, and vertical line by tilting the reflector sideways, not the reading. Then shift the reflector to the next position, again adjust and take the reading up to the end of the surface. So the tabular column is like this. This is the position. Position means the position of the reflector. 0 first phase, then 0 to 50, 50 to 100, 100 to 150, like that. So we get the reading in second here. Second, 20, 50 to 100, 18, like that, these readings. Then this column kind is difference from first reading. Take first reading as a reference, deduct this reading from the all other readings. Here this is already 0 because this is vertical to the optical axis. Arbitrarily you write 0 here. Then you are going to take the reading for the first position 0 to 50. That is 20. So this position 20 minus 20, 0. Then 18 minus 20 minus 2, 16 minus 20, 16 minus 20 minus 4, 10 minus 20 minus 10, like that. Deduct the first reading from all other reading. So you get the deviation with respect to the first reading. So this is in second. This reading is in second. The difference is also in second. So we have to convert this into linear displacement. So for that, riser for this base is previously calibrated for 1 second tilt of the reflector. The value is 0.25. That is already calibrated by the company, and the value is 0.50 mm base. 0.25 is the micron is the linear displacement. So this is 0, 0 into 0, 0, 0 into 0.25, 0, minus 2 into 0.25, 0.5, 0.4 into 0.25, 0.1, like that. Multiply all this reading into 0.25. So you get this in micron, difference in micron at each position. Now, so this different rise or fall with respect to the position, you get a graph like this. This is the carriage position, and this is the rise or fall, like this. So this is the last point is shift. This is the horizontal axis, and last point is here. This is this much deviated from the reference line. This is minus. Okay, we have to find out the cumulative rise or fall. Cumulative, to find out the cumulative means the last point deviation. Last point deviation. Last point deviation means add this cumulatively. Add all the reading cumulatively. 0, 0 position, 0 plus 0, 0, 0 plus 0.5, 0.5, 0.5 plus minus 1, minus 1.5, minus 1.5 plus 2.5, minus 4, like this. So the cumulative rise or fall you will get like this. This is minus 10. So actually the graph is carriage position plus on this x-axis and y-axis cumulative rise. Cumulative, no, not this. Previously I told this one, not this one. This cumulative. Y-axis carries cumulative rise or fall. So you get the cumulative shift of the last point from the datum horizontal line. This much it is shifted from the datum line. So we have to find out the error, you have to shift this line, this point to datum line. So you have to add a correction factor at this point. And what is the correction factor at this point? This is minus 10. So here we have to add a plus 10. Similarly, we have to corresponding value, we have to add a correction factor at each point, so that this point reach here and this point reach shift from this position like that. So for that you have to divide this position, this cumulative cumulative value divided by number of position. So this you are taking 10 reading in this case. So this is divided by 10, minus 10 divided by 10, you get minus 1. Take the opposite sign, plus 1. Add plus 1 at each point, plus 1 at each point. So that initial point 0 and last point here in minus 10, this will plus 10. So this is the data line, this is already 0. Then this reading is 0 to 50. 0 to 50 you have to add 1. So correction factor is 1 at each point. You add 1 plus 1 cumulatively. So 1, so this will shift. Again plus 1 plus 2. Again this will shift. Then plus 3 shift. So finally this will reach here. So this will reach here. So this 0 0 on the datum point here, minus 10 add plus 10. So this is on the datum term. So by adding these two, you will get the error at each point. 0 plus 0, 0, 1 plus 0, 1, minus 0.5 plus 2, 1.5 like plus 1.5 like that. So these are error at each point. So to specify the straightness of the surface, you take the maximum minus deviation and maximum plus deviation. Here maximum 3.5. Plus deviation is 3.5, minus deviation is minus 1. So 4 micron is now the 4 micron is a straightness error of the surface. 4 micron. 4 micron means within two horizontal line, two reference line with a gap of 4 micron, the surface in which the surface lies. So that is the straightness error. If you want to find out the flatness, you have to take minimum two sets of straightness, one along the x-axis like this and one along the y-axis. So after taking the reading, you construct a reference plane, then from that plane you can find out the flatness error, two plane surface within which the surface rests. That is the flatness error. This is in our case it is straightness error. So to begin with the experiment, you have to adjust the screw, this base screw, so that there is a bubble. This comes within the spirit level. There is a bubble or a circle inside this. Adjust this one so that this will comes within the circle, and then align the reflector in front and see whether the reflector light is coming. Before adjustment, in the eyepiece field you can see the two different eyepiece graticule and separate target graticule separately. Now you have to coincide a vertical line with the vertical line and horizontal line in between the twin horizontal line. So for that, for coinciding the horizontal line, you have to rotate the micrometer head. So now you can see that is coinciding with this horizontal line of the target reticule in between the twin line of the eyepiece reticule. Now we have to adjust the vertical line. But for vertical line we have to tilt to the sideways. Two vertical line coincide. You have to adjust the micrometer head so that horizontal line of the eyepiece reticule coincide with the horizontal line of the target reticule. So this is the adjusted position. You can see the adjusted position. Horizontal line of the eyepiece reticule. Okay. Horizontal line of the targetic reticule in between the twin line of the eyepiece reticule, and vertical line of the targetic reticule coinciding with the vertical line of the eyepiece reticule. This is the adjusted position. Now it is ready to take the reading. So this is the main scale, this is the head scale, and this main scale one division is 0.5 degree. This is in seconds. 0.5 divided into 30 seconds. So 0.2 second is a one division here. So now this is here 0, 5, 6.5 here, 6.5 degree. This is 27.2 minute. 0 to 50 position. 0 to 50 reading 6.5 degree 20 reading 27.2 minute. 6.5 degree here. This is 27.2. This is not degree, minute. 6.5 minute, 27.2 second. Minute, second. Now again shift the reflector to the next position. 50 to 100. 50 to 100. Shift this edge to here, 50 to 50, this edge to 50, 5. So this is 50 to 50. Again you align the reflector. Adjust the vertical line. Then adjust the horizontal line. Horizontal line is adjusted. So like this. Then note the reading. This 0.5 minute. One by minute 7.6 second. 7.6 second. So like that, you proceed to take the reading by shifting again to the 100 to 150 mm. Again adjust the reflector and take the reading till the end of the surface. You proceed the experiment and note all the readings. Then from this reading you plot the readings in the chart, and then like this you find out tabulate all the reading and find out. Firstly you have to position on this readings only you have to take. Then after that you calculate all these values from these readings. Difference from first reading, then rise or fall. By multiplying this reading with 0.5 micron. Then find the cumulative rise or fall, so that you will get the displacement of the last point from the datum line. Then you have to shift this to actually this is the reference line. You have to shift this to this datum line. For that you have to add a correction factor. So divide the last cumulative point divided by number of position. Here minus 10, so divided by 10 position, so divided by 10. So you get minus 1, add opposite sign value plus 1 at each point from the 0 point position, first position. So that this 1, 2, 3 up to 10. Here these 2 points carry 0, this minus 10, opposite plus 10. So this also reaches after adding the correction factor, this reaches the datum point. Now by adding these two, cumulative rise or fall plus adjustment required, we will get the error at each point by adding this two. This is the error. So you find out the maximum deviation to the bottom surface and the top surface. By adding that, you will get the straightness error. So within that line, the full surface remains within that two lines. Here it is 3.5 plus minus 0.5. So 4 micron for this reading is 4 micron. So like that we can find out the straightness error of the surface. So this is surface plate, and similarly you can find the straightness error of a lathe bed and aligning a roller machine. Everything like that we can use industrially. We can use the autocollimator for align purpose also.